Hello, my darlings. All right, so today we're going to look at an application of the integral to motion. Here we go. One of the basic concepts in integral calculus is that the integral of the rate of change of a quantity can be used to find the net change in that quantity over a period of time. For example, if f of t is the production rate of an item in units per month, or t is in months, then the integral from 4 to 12 of f of t dt is equal to the number of units produced between t equals 4 months and t equals 12 months. So our integrals can be applied to find net change. Now today, we're going to concentrate on applying that net change to motion. So there are three main question stems that can happen with these motion problems that involve integrals, okay? If you're given the object's velocity, so for instance, I have a velocity graph here, and a question stem is asking about the object's position, we need to understand which definite integral we need to use. So it depends on what they're asking us to find. Now displacement, remember, that's just the change in position. That's where you're going to take the integral from a to b of your velocity function, because what that does is it takes the area of region 1, subtracts off the area of region 2, and adds the area of region 3. So it tells us how far to the right we went, then how far to the left we went, and then how far to the right we went again, and adds up and subtracts so we find the distance between the beginning and our end. That's what it's going to do with just the integral from a to b of v of t dt. Now, if we want the total distance traveled, we want to take the area of 1, add the area of 2, and add the area of 3. So that's a different integral. It's still the integral from a to b, but this time it's the absolute value of v of t dt, so that we pop this region a of t positive above the x-axis. Now, if we want to know the actual position of a particle, remember, the integral from a to b of v of t tells us how far it's moved, right? But if I add its starting position, that will tell us where we ended up. So where C is the initial or the starting position. So let's try an example to see how that works. So given that s of 0 is 4, and the diagram of the velocity function here with these areas marked, find displacement, total distance traveled, and position from 0 to 10, where velocity is measured in meters per second. So the displacement is how far we've moved from the beginning to the end. So that would be the integral from 0 to 10 of v of t dt. So if we look at our graph, from 0 to 5, we went 18. Now from 5 to 10, we moved 12, but it's negative because it's below the x-axis. We subtract, and we get 6, and our unit is meters. Okay, awesome. Now total distance. Total distance, we integrate from 0 to 10, the absolute value of velocity, right? Because we don't care which direction we're moving, we just want to know how far we went. So it's the absolute value, which means we still have 18, but we're going to add the 12, and now we have 30 meters. Big difference between displacement of 6 meters and total distance traveled of 30 meters. Now the position at time 10, remember, we know that the position at time 0, so we can do s of 0 plus the integral from 4 to t of any velocity, of the velocity at any time to find the position, okay? That's how we would find the position at any time. So we want s of 10, that's going to be s of 0 is 4 plus the integral from 0 to 10 of v of t dt. So that's 4 plus, now wait a minute, we already did this integral from 0 to 10 of v of t dt and got 6. So 4 plus 6, that's 10 meters. So our position, we are at position 10 meters after 10 seconds. Okay, so we're back to the nut strategy, interpreting motion in integrals here. So remember, the position of a particle is moving on the x-axis in feet from the origin, okay, is given by x of t. Then we know that the velocity of the particle in feet per second is given by v of t. And we know that the acceleration is given by a of t. Okay, we're going to use this information now so that we can, for each of the integral expressions that's coming up, given in the following table, we're going to interpret its meaning by filling in the missing noun, the appropriate units, and/or the correct value of time or the time interval. Okay, so noun, units, and time. Here we go. So now we have x of 2 plus the integral from 2 to 4. Notice this x of 2, this is our lower limit. That's an initial position. And also, we have the integral from 2 to 4 of x prime of t. That's the velocity function, remember. So this is the position of the particle in feet from the origin. And they've told us that the time was at 4 seconds. Notice that's the upper limit. Now the next one is the integral from 1 to 4 of x prime of t dt. And again, remember, that's the integral from 1 to 4 of v of t dt. So that's the change in position of the particle. That's also measured in feet. And when is that happening? That's happening from t equals 1 to t equals 4 seconds. All right, now look at the next one. 1 over 4 minus 1 times the integral of 1 over 4. That's an average value. And it looks like it would be velocity, but it's not average velocity because what is the absolute value of v of t? That's speed. So this is the average speed of the particle. And notice the units were in feet per second, which means you would have been between velocity or speed. And this is happening between time equals 1 and time equals 4 seconds. And don't forget the unit on that time. All right, next up, we have x of 4 plus the integral from 4 to 2 of v of t dt. Notice the lower limit, and we have the position at that lower limit. That's taking the starting position plus our change in position. That is the position of the particle. That's measured in feet from the origin, and it's happening at the time t equals 2 seconds. Next one, the integral from 1 to 4 of the absolute value of v of t dt. That is total distance traveled by the particle. So be really careful with the difference between these two. Once you put that 1 over b minus a, now you're not total distance, it was average speed. So be really careful between the difference of those. So this total distance is also measured in feet from the origin, and so is the second one. We should be specific, huh? All right. And the last one, 1 over 4 minus 1 times the integral to 1 to 4, that's an average value. And notice this is a of t, so it's average acceleration of the particle. That's going to be in feet per second per second. Yes, that is the same as feet per second squared. And that is happening between t equals 1 and t equals 4 seconds. Okay, now let's look at a motion problem given a graph. So we're going to look at a graphic problem. So we're given the graph of v of t. The graph at the right represents the velocity of a particle that is moving along the x-axis on the interval from 0 to 8. V of t is measured in inches per second. So for what interval or intervals of time is the particle moving to the right? If the particle is moving to the right, the velocity has to be greater than 0. So where is that happening? Anytime the velocity is above the x-axis. Okay, so that means the particle, and notice it says justify, so we have to be careful here. The particle is moving to the right on 0 less than t less than 3 and 7 less than t less than 8, since v of t is greater than 0, or if you would prefer to write, or since velocity is positive. And in this case, it doesn't have to be equal to 0 because we're not looking for when it's stopped. All right, next up. On what interval or intervals is the particle slowing down? And justify. Now, the particles will slow down. Let's think about when this happened. The particle will slow down when velocity and acceleration have different signs. So remember, acceleration is the slope of this graph. So when the graph is above the x-axis, velocity is positive. So if we're above the x-axis, the velocity is positive, and we would need acceleration to be negative, which means the velocity would be decreasing. So that happens here. It's the only place where velocity is positive that this happens, between 2 and 3. Now, the other option is when velocity is negative, so below the x-axis. Now, if velocity is negative, we would need acceleration to be positive. That means a positive slope, and we'd have a positive slope here. There we go. So now we know what our answers are. We just have to write it out. So here we go. The particle slows down. On our first interval was 2 less than t less than 3, since the velocity is greater than 0, it's above the x-axis, and the velocity is decreasing, which remember means that the acceleration is negative. And on the interval, where did we say? From 6 less than t less than 7, since this time the velocity was negative because it's below the x-axis, and velocity is increasing, which means that the acceleration is positive. There we go. Okay, here's another one. When is the particle stopped? That means the velocity is 0, and changing directions. That means the velocity has to change signs. That means we cannot use times 0, okay? Cannot use times 0. But we can use times 3 and times 7. So here we go. The particle, because again, it says justify, be very careful, and specific. The particle is stopped and changing direction at t equals 3 and t equals 7, since v of 3 equals v of 7 equals 0, and the velocity changes from positive to negative at t equals 3, and the velocity changes from negative to positive at t equals 7. Okay. Next part, next and last on this problem, on what time intervals is the acceleration 0? And justify your answer. So now remember, acceleration equals 0 when the velocity is constant or horizontal. That happens here and here. So this happens on 1 less than t less than 2, and from 4 to 6, so 4 less than t less than 6. And there we go. Ta-da! All right, just a reminder here before we go to the next problem. Some motion problems will require you to find the actual position of an object or particle at a given time. Remember that you will need to use the initial conditions in order to find the actual position, because the definite integral only provides the change in position. So the integral is the change in position of the object, or the displacement. But if we add an initial condition, that gives us the actual position. Okay, so now we have a problem. It's a calculator problem. And here we go. It's also an analytic problem. So we have the function itself. So an object moves in a straight line with velocity v of t equals the square root of 3t minus 2 meters per second, where t is time in seconds. At t equals 5, the object's distance from the starting point was 12 meters. Okay, so now we want to write an integral expression that will compute the object's position at t equals 10 seconds. So what we do is we need the initial position plus the displacement. Well, the initial position is 12 plus the displacement is the integral, because 12 is over here, but when did that happen? At time 5. That's why this is here, okay? And since we want to go up to time 10, that's our upper limit, and our velocity function is the square root of 3t minus 2 dt. And yes, it's okay if you write 12 plus the integral from 5 to 10 of v of t dt. Okay, they are both fine, either way. Okay, so that's our answer for part A. Now, part B is to use our calculator to actually find the value. So we're going to go to our calculator and we are going to type all of this into the calculator. Okay, so here we're going to type 12 plus, go to your template key. We need our integral, the definite integral, choose that. We are going from 5, tab up to 10, tab over into the integrand, control x squared for the radical, 3t minus 2, tab out of the radical, tab over to the differential, dt, press enter, and there we go, 35.508868, so 34.509 meters. Okay, so now let's try another one. A particle is moving along the x-axis with velocity v of t equals negative t squared plus 7t minus 10, measured in meters per second after t seconds, with an initial position of s of 0 equals negative 3. So we want to determine the displacement of the particle on the time interval from 1 to 7. So displacement is the simple integral, the integral from 1 to 7 of our velocity function, which is negative t squared plus 7t minus 10 dt. Now this one is not a calculator question, so we have to take the antiderivative. So we keep the negative, add 1 to the exponent, divide by that new exponent 3, plus keep the 7, we have the t, add 1 to the exponent, so it's 2, divide by that new exponent 2, minus the antiderivative 10 is 10t, and we're going to evaluate from 1 to 7. So now, when we substitute in, we're going to have the negation of 7 cubed is 343 over 3, plus, well, 7 times 7 squared is 7 cubed again. That's 343 over 2, minus 70, minus, now we substitute in the lower limit. So that's going to be negative 1 cubed plus 7 halves minus 10. Now remember, we're going to make this plus and change all the signs behind it. Okay, so that means we've got negative 342 over 3 plus 336 over 2 minus 60. And then if we divide, 3 goes into negative 342, negative 114 times. 2 goes into 336, 168 times, and we still have minus 60. Add and subtract, and we will get negative 6 feet. So we have a displacement of negative 6 feet from the time 1 to 7. All right. Now, same problem, but we want the total distance traveled by the particle on the same time difference. Okay, so we know the displacement when they are 6 feet to the left of the origin, they're at negative 6 feet. Now we want the total distance traveled. So here we go. Now here's the problem with total distance traveled without a calculator. How do you integrate the absolute value? Because we know total distance is going to be the integral from 1 to 7 of the absolute value of v of t dt. But it's not a calculator question. It's really easy if I can throw it in a calculator. However, I do know that this velocity function is a parabola that opens downward. So it starts below the x-axis and ends below the x-axis, but it's above in between, right? So what we need to do first is we're going to take this velocity and we're going to factor it. I'm going to factor out the negative first. And then I know that's going to factor to t minus 2 and t minus 5, which means that the velocity is 0 at t equals 2 and t equals 5. That is where we're going to need to break up our integrals. So our total distance, which is the integral from 1 to 7 of the absolute value of v of t dt, is going to become, and you know what, we'll do this so you don't even know when it's upside down or right side up. Let's pretend you don't know. The integral from 1 to 2, just in case you get one where you have to, of the absolute value of v of t dt, plus, then we're going to do the integral from 2 to the other x-intercept 5, absolute value of v of t dt. So anytime you have a function and you don't know what it looks like, you find the x-intercepts and break up the integral at those x-intercepts, taking the integral of the absolute value of each part, okay? Plus, and we still have to go from 5 to the endpoint 7 of the absolute value of v of t dt. Okay, now we've already done the antiderivative of v of t dt. We did that before. We know that it's negative t cubed over 3 plus 7t squared over 2 minus 10t. But we're evaluating from 1 to 2, and we're taking the absolute value of this. Plus, we're going to take the same antiderivative, negative t cubed over 3 plus 7t squared over 2 minus 10t, and we're going to evaluate from 2 to 5, and we're going to take the absolute value of this, and we're going to add the same antiderivative, negative t cubed over 3 plus 7t squared over 2 minus 10t, evaluated from 2 to 5, and we're going to take the absolute value of it. Oh, doesn't this look like fun, my darlings? I will be honest, the arithmetic is absolutely ridiculous, okay? So I'm going to let you go to your calculators right now, plug those numbers in. Remember, you're going to substitute in the 2 first. So you're going to have the absolute value of negative 2 cubed over 3 plus 7 times 2 squared over 2 minus 10 times 2, close it, minus, open, plug in the 1, negative 1/3 plus 7 over 2 minus 10 times 1, close it, absolute value closed, plus absolute value open. We're going to plug in the top, negative 5 cubed over 3 plus 7 times 5 squared over 2 minus 10 times 5, close it, minus, now substitute in the bottom, negative 2 cubed over 3 plus 7 times 2 squared over 2 minus 10 times 2, close it, close the absolute value. We're not done. Plus the absolute value of, substitute in the top. Oh no, my limits are wrong on that last one. Hold on. Those limits should have been from 5 to 7, right? That was here, 5 to 7. Okay, so we're going to substitute in a 7, so it's negative 7 cubed over 3 plus, that's also 7 cubed over 2 minus 10 times 7. Close it, minus, Open, negative 5 cubed over 3 plus 7 times 5 squared, all over 2 minus 10 times 5. Close it, absolute value. Go grab your calculators, guys. If you grab your calculators, you're going to see that we will have the absolute value of a negative 11 over 6 plus the absolute value of 9 halves plus the absolute value of negative 26 over 3, which will give us 11 over 6 plus 9 over 2 plus 26 over 3, which means we have a least common denominator of 6. The 11 doesn't change. We had to multiply the 2 by 3, so 9 times 3 is 27. We had to multiply the 3 times 2, so 26 times 2 is 52. Add that up, it's 90 over 6, which gives us 15 feet. The hardest part of this one was the fractions. Okay, I promise not to give you one with that many fractions on a test or a quiz. All right, unless it's on the calculator part. All right, my darlings, so we have looked at an application of the integrals to motion. Make sure you understand the difference between how to find position, how to find total distance traveled, and how to find displacement using your integrals. Have a great day, guys.